Okay, so chapter 7.1, solving systems of linear equations graphically. Um, Hopefully everyone did okay on that test, on the chapter 5-6 test. And now we're going to continue with linear equations, but now we're going to be solving them. Well, when I mean solving them, say you have two lines, two slopes. We're going to find the point that they intersect, or the point that they cross at. Okay. So let's jump into it. I'll go over the completed this notes this time, and I'm trying to keep and changing it up every time. Sometimes a textbook, sometimes I write the notes, or sometimes I'll go over the completed notes. Let me know what you prefer. Maybe I'll stick to one method. Okay, a system of linear equations is two or more linear equations involving common variables. Okay, solving a system of linear equations involves finding the point at which the lines intersect, if at all. This can be done graphically or algebraically. So we're going to go over both methods. So graphically, you can just draw the two lines on a graph, obviously, and then you see the point that they intersect, and that will be your answer, right? If they don't intersect at all, that means there is no answer, or it's not you can't solve that equation. We're going to be looking at the equations in the form y equals mx plus b, or the slope-intercept form. So if you get an equation that doesn't look like that, you can just use some algebra and convert it to y equals mx plus b, and then you just graph the two lines. Okay. Algebraically, you're gonna find out all we're gonna do is you just plug in the point that they give you, and you see if the left side equals the right side for the equations. If it does, that means that point does lie on that slope. Okay, and then you have to do the other equation too. The second equation, the point given, you solve by plugging in the x and y that's given. And if the left side of the equation equals the right side for that one as well, that means that point lies on that slope. And that means they intersect at that point. Okay. All right, so let's jump into it. Example 1. Solve each system of linear equations graphically, then verify your solution. Okay. Okay, so in this example, obviously it's done here, but I'll kind of explain what's going on here. So you got two equations, and you can see it's in the form y equals mx plus b. Here's the slope again, as a reminder. And the b here, this is the y-intercept, right? So we have two equations, and to graph them, again, you just start from the y-intercept. So the first one is plus 7, so you up 7 to right here, do a point. And then once you got the first point on the y-intercept, then you just use a slope to extend it out. So rise over run, 1 over 2. So up 1 over 2, up 1 over 2, right? And then once you have like 3 points, you use your ruler, and just draw a straight line. And then you got our first slope. So second slope, same idea. Here, the y-intercept is -3, so the main vertical axis, you go down -3, 1, 2, 3, do your point. And you know it's going to go from top left to, well, really not top left, but from upper left to bottom right, because it's negative slope, right? So rise over run, but instead we went up and right, we go up and left when it's negative. So up 2, 1, 2, and over 1 point, up 2, over 1 point. Okay, and then you draw a straight line. So you can see graphically, at this point here, they intersect, so this is going to be the solution of the equation. So when you draw graphically, make sure you label your two lines so you don't get confused with the equation here, and you label the point that they intersect. So here, the x is -1, 2, 3, 4, not 5, 1, 2, 3, 4, 5. So they intersect at point -4, 5. Okay. Once you do that, you can also verify your solution just to make sure you're correct. So to verify it, you just use this x and y point and you plug it back into the original equations. So you have to do it for both, okay? So do it for the first one, right? Plug in -4 for the x and 5 for the y. So you can see that's what they're doing here, right? They're plugging into the equations, and as long as the left side equals the right side, that means it's verified. I mean, it works. Okay. So eventually, when you do the math here, 5 equals 5. So same thing here with the second equation. You plug in that point -4 for x and 5 for y, and then the left side equals the right side, verified. Yeah. So same sort of thing here. So in this example, they give you two equations. It's not in the form of y equals mx plus b, so what do? You just move everything over except for the y. Make sure the y is on one side positive. to get it into the form of y equals mx plus b. So negative 2x here, negative 2x here, and then you get y equals 2x minus plus 3. Second equation, x plus 2y equals negative 6y. So again, minus x here, then divide this by 2. That means you have to divide everything else by 2, which they're doing right here. And then you get the equation y equals negative half x minus 3. Okay, so I'm sure you know how to graph this. So exactly the same way that we did on the left, start with the y-intercepts, and then you just use the slopes, right? And once you get a couple points, draw a straight line. And you can see that they intersect at this point graphically. So you'll label that point. Here they got 4, negative 5. And now you just need to verify the solution. So plug this in and plug it into the original equation, right? Don't plug it into the algebraically modified one that you did to make it look like y equals mx plus b. Because this is just, it's good habit to use the original equation, because you might have made a mistake, you know, doing the algebra. If you make a mistake, then if you plug this in, it might work for your equation that is not right, right? So you want to make sure it works for the original equations. So you plug it in for both of them, and you just check it to see if the left side equals the right side. So plug the intersecting point, the x and y coordinates for the x and y, and then if it does work out, that means it's correct. Okay. Example 2. Is this given point a solution to the system of linear equations? Okay, so for this question, again, they give us 2 equations, and the solution of the system of linear equations. A system of linear equations just means 2 or more linear lines or straight lines, and the solution is a point where they intersect. So we've got 2 equations, and we have this one point that they're asking if they're seeing if this is a solution for 7. So what do we have to do? You just plug it into both equations, and it needs to work for both. Okay, if it works for one and not the other, it's not a solution. It has to work for both equations. So we plug in the 7 for y and 4 for x. Do the first one, and the first one, when you do it out, you already see it says 7 equals 33, which is not correct, not true. So this point doesn't work for the first one. You don't even need to do the second one, because if it doesn't work for one, it doesn't work for the solution. It's not a solution for the system of linear equation. Okay, so that one's no. Same idea here. You just plug it into the first equation, plug into the second equation. Here's the algebra here. Maybe we'll just talk about this one right now. So x is negative 5, so plug the negative 5 there. So negative 5 times 4 gives you the negative 20. The y is negative 8, so negative 8 times negative 5 gives you the 40. And the other side of the equation, we just have that 20 there. And then negative 20 plus 40, 20 equals 20. So it works for the first one. And the second equation right here, we plug it in again, negative 5 for the x, and negative 8 for the y. So negative 8 times 3 gives you negative 24, negative 24, negative 5, negative 29. And the other side of the equation is negative 29, so it works. It works for both, so it's a solution. Okay. So you can go through the steps of the algebra. It's exactly the same. Plug in the points, x and y coordinates. It works for the example C. And example D, this is what I mean. So in this example, it didn't work for one of the equations, but it worked for the other. So let's take a look here. So the first one, it didn't work when you plug it in. 4 times x, so x is 1 in this case, is 4, and y is 0, so 4 times 1 plus 0 is 4. 4 does not equal 6, so it doesn't work for this one. But for the second one, if you just did the second one, you can see if we plug in x, 1 minus 0 is 1. So it worked, 1 equals 1. So the second one, it worked. But if we only did the second one, we might think it's the solution, but we need to check the other one as well. Okay. All right, so we got example 3 here. May graph the system of linear equations y equals 3x plus 4 and y equals negative 2x plus b. She knows that the solution is 210.210. What is the value of b? Okay, this is pretty simple. So you have your point, and it says that this is a solution for sure, right? That they're basically saying that she knows is a solution. And so that means if you plug the x and y for this point here, or this equation here, then you have the y, you have the x. We'll only have one variable. So as long as you have everything else figured out, you can just isolate for the b. And that's what they do. They use that equation, and then they solve for b. You don't even need this equation here. You're just using the one over here. Yeah. And eventually get b equals 14. All right. So example 4, graph the following 3 lines on the grid. Okay, so by now, hopefully, since we did chapter 5 and 6, graphing is pretty straightforward. Hopefully you got that down now. And well, that's not true. It's not really straightforward. Sometimes it can get confusing, but hopefully by now you got a grasp on it. So on this equation, of 3 equations, what I would do, or what you should do, is first turn it into the form y equals mx plus b. So that's what they're doing here. They're just doing some algebra, shifting some things over, make sure y is positive one side and everything else to the other side. And once you do that, then if it looks like y equals mx plus b, then you know the slope and you know the y-intercept. Then you can graph it pretty easily. Okay, so you can do that for both on all 3 actually. So here, equation 3 might be tricky. So x equals -3 when you move it over. So this case you should know is a special, I guess, a special case where it's a vertical line. So x equals -3. So x, if you can see here in this vertical line here, because this all these points is x equals -3, right? If it's y equals -3, then it would be a horizontal line, right? That's a case of horizontal line. Okay. But anyways, you get your 3 equations, and you just label them. Here, they just label it 1, 2, 3. So that's part A. Part B, a triangle is formed by these 3 lines. Okay, so yeah, you can see right here the triangle. Determine the coordinates of the vertices of the triangle. So this is just, once you've graphed it, you just read off the grid, right? So if you read off of it, you'll get these values here. So you can check that out. Yeah. That's it for example 4. Yeah. Example 5, I think this is the last question, so there's a word problem here. So let's read this and we'll go over what this paragraph means and we'll see what they did on the graph here. So Sam and Malik go skydiving together. Terminal velocity, yeah, it says max. So terminal velocity is basically, say you're free falling. In this case, they're going to be free falling from the sky. At a certain point, like you're going to go faster and faster, but at a certain point you reach the maximum speed. And that's known as your terminal velocity. You don't keep going faster like to infinity, right? So at some point, due to like air resistance and drag, you're gonna start slowing down, and then you're still gonna be falling down fast, but your velocity is not gonna be increasing anymore. Yeah. So anyways, back to the question. Terminal velocity occurs during free fall when the air resistance causes the body to fall at constant speed. Okay, there you go. Sam reaches a terminal velocity of 50 meters per second at an altitude of 3,000 meters. There's no velocity. It's always meters per second, and velocity is a little bit different. Again, this is not part of the question, but velocity is different than just speed. Strictly, speed is just a magnitude, an amount, right? Like how fast are you going? Like 50, you know, whatever the speed is. But velocity has a direction to it, so it's gonna be the how the speed of it, but also in a certain direction. Here, the direction is going to be going downwards towards Earth because it's a free fall case. Okay. Okay. Anyways, the distance d in meters above the ground at time t in seconds after reaching terminal velocity for each person is modeled by the following equations. Okay, so we got 2 equations here, and so Sam and Malik are both falling, and Malik reached a terminal velocity at 50 meters per second at 3,000 meters, and Malik reaches a terminal velocity of 40 meters per second at 2,600 meters above the ground, right? So it looks like Sam's going down a little bit faster, but Sam is also higher than Malik, right? Okay, so there's 2 equations. So this is the equation. So d equals -50t plus 3,000. And t, they said, is going to be the time in seconds. D is the distance. So this equation is just representing it's representing their distance from the ground and how much time has passed, right? So in this case, 3,000 meters is going to be, I guess, their 3,000 meters is like the distance from the ground that they reach the terminal velocity. Okay, so at 3,000 meter was Sam, and 2,600 meters was Malik. Okay. Graph the system of linear equations. So this may not look like y equals mx plus b exactly, just because we're not using y and x, but you can see how similar it is, right? So in this case, a -50 is going to be the slope, and the 3000 is going to be the b or the y-intercept. Okay, same thing for Malik as well. So on a graphing paper now, the tricky thing might be just actually to set it up. Okay, so you might get a blank graphing paper. How do you know how to label the y-axis? Okay, so first of all, you know that they're going down. So they're starting from 3,000 meters from ground level to where they are, and they're going to go closer and closer to Earth. So 3,000 can be the very top because they're not going to somehow magically go upwards, right? So then you can just space out your graph, your section, from 0 to 3,000. That's what's done here. Make sure, again, a review is on graphing, make sure your y-axis is labeled, distance in meters. X, see the horizontal axis is going to be time again because it's an independent variable, right? Always on the x-axis, and you have the units as well. Okay. Okay. So, okay, then once you get this, time might be a little bit more tricky to kind of know exactly what to put. But yeah, so you may need to edit like the time if it doesn't look right. You could also, when you want to create your graph, you can also create a table of values as well, and just input maybe 3 or 4 points for D, like test out what time is for 3,000, what time it is for 1,500, what time it is for like 500, and then you'll know estimates for time, and then you can space this out. Okay, if you want to do it that way. Okay, so once you get that, and then you're just gonna graph it out. So again, start from the y-intercept up here for Sam. Yeah, so 3,000 meters for Sam, and then you do the slope. This is over 50. Rise over run, sorry. So down 50 because it's negative, and over 1, down 50 over 1, down 50 over 1. But you can see it's 3,000 to 1,000, or 3,000 all the way to 0. So going down 50 over 1, down, down. It's going to take a long time to draw this slope. So what you could do here is you could just multiply the 50 over 1 by 10, the slope 50 over 1, negative 50 over 1. So negative 50 over 1 is the same thing as negative 500 over 10. So we can do that, it might fit better. So you go down 500 units and then over 10 seconds. Down 500 units, over 10 seconds. Down 500 units, over 10. And that's how they got these points here. Yeah. And then once you get that, 3 points for each line. Do the same thing with Malik. It's Malik starting at 2,600 for the y-intercept, and you're going down 400 over 10, down 400 over 10, down 400 over 10. The point that they intersect, that's going to be the solution for this system of linear equations. Okay, so that's all you're doing here. So we talked about labeling and all that. So hopefully this section made sense. Okay. Okay, so determine the point of intersection of two lines graphically. So once we've done the graph, just for the point that they cross or intersect, that's going to be the solution. So here we go. So 40,000 meters. So 40 is, again, representing the time. At 40 seconds, they're at 1,000 meters. So at 40 seconds, they're both at 1,000 meters above the ground, right? That's all that's saying. What does this point of intersection represent? Okay, we just talked about that. So after 40 seconds of each falling at terminal velocity, they are both 1,000 meters from the ground. Okay, and that's pretty much it. Okay, so you could have, this equation, you could have solved it algebraically too. You got two equations, two unknowns. You can just isolate for, well, these are already isolated. So this equation here, you can just plug it in over here, and then you could solve for t, right? But obviously they don't want us to do that in this equation. They want us to do it graphically. And in a future lesson, we're going to do the algebraic way. So, and that's that. Today's going to be, I think this will be it for the notes today, about 20 minutes. Because you also had a test, and I think after doing a 2-3 hour test, 20 minutes of notes, and then also have the homework for this section, I think that'll be enough. And then tomorrow we'll continue with 7.2 that we're supposed to do today. We'll do 7.2 tomorrow, and we'll do, is there 7.3? I think there's 7.3, then 8.1. Yeah. All right.